So thank you, Vida, and thank you all for being here, and thank you to the people, the Zoomers, also for being there. Look, I mean, so I'm in Toronto, and Toronto feels like home. So it's really a great pleasure to just be able to talk to you and introduce the research that we do in the group. I'll be here for a few months, so help me go to a highly non-equilibrium place. Talk to me about what you're talking, what you're thinking, your desires in terms of science. I'm really, really happy to talk. Okay, so I would like to just say that essentially I'm across the lake from you, no? In Rochester, it's almost it's really just south of here, and this is the University of Rochester right here. This is the Lake Genesee. That's the city of Rochester, and that blue thing at the end is Lake Ontario. That's what divides us between Toronto and Rochester. Technically, we are the land of the Kodak moment. For those of you that are old enough to get the idea. Okay, so let me just start with something that I know many people in this room care about, which is quantum mechanics in chemistry. So molecules are pretty amazing quantum systems, no? They have manifolds of transitions in many regions of the electromagnetic spectrum, and the energy levels can be chemically tuned. They can be assembled into complex architectures. And for this reason, you can, in principle, do quantum operations in a variety of timescales and control them chemically. And ever since the inception of quantum mechanics, there has been a dream in the chemistry community of how do we use quantum coherence and other non-trivial quantum mechanical effects to enhance molecular function. And that dream has taken many forms over the years. This is a book by Paul summarizing his ideas in this context. This is a more recent review, and so on and so forth. So there has been, it's a long-standing topic in chemistry. And my group really cares about this idea. And we work in 4 different directions right now. We work in the problem of how do we control matter at the level of electrons using ultrafast laser sources, because we have to think about quantum coherence and quantum control. We also have to think about how to protect that quantum coherence. No? So we work a lot on understanding the coherence processes in molecules. We have to simulate these processes, and for that, we work on quantum simulation, both in digital simulation and now in analog quantum simulation. And in a topic that we share with Vida quite heavily, it is the idea of quantum transport. So we also work in the theory and the simulation of quantum transport and molecular electronics. And today, what I would like to focus today is on 2, what I think, emerging topics. The idea that we can use lasers to drive electronics to the petahertz limit. This is about 6 orders of magnitude faster than the state of the art. And I would like to tell you about our progress in developing tools for quantum simulations, but analog quantum simulation of chemical dynamics, in which we map the dynamics of interest into a highly controllable quantum hardware. Okay. So let me start with the idea of controlling matter at the level of electrons. So the reason why we focus on electrons is because if you're able to control electrons, you can control the optical properties of matter, the transport properties of matter, and eventually the chemical reactivity. And the reason why we are interested in controlling electrons using coherent laser sources instead of conventional means, and by conventional means, I mean an applied voltage, thermodynamic or chemical control, is because if you're able to do it with lasers, you are able to do it very fast on a femtosecond timescale. Okay, so with this idea in mind, over the last 9 years or so, we have developed 3 essential strategies to control electrons in matter. We have developed strategies based on the Floquet engineering, in particular of optical property. This is a direction of active research in my group right now. We have developed a general scheme to control electrons across the interfaces based on the Stark effect. The advantage of this scheme is that it's robust to decoherence. And the topic that I would like to discuss today is a topic that actually started here for me as a PhD student, which is the problem of inducing currents along nanojunctions using lasers. And I would like to tell you where are we at that time, okay, in that topic. Okay, so what's the idea? So you have nanoscale junction, so where you have a metal here, another metal there, and some material in the middle. That material could be a dielectric, it could be a semiconductor, it could be a molecule, it could be a semi-metal. The system is spatially symmetric. There is no bias voltage. And what we're going to do is that we're going to come in with a very special class of laser fields, break the spatial symmetry, and generate currents. And if we're able to do that, what we'll be able to do is to generate bursts of currents on a femtosecond timescale, which is essentially a new current standard. Okay. What are the main physical ingredients? So what you need for this are two things. You need a field, a laser field that has a low temporal symmetry, and I'll tell you what I mean by this. And you need the nonlinear response of matter to that laser field. And the traditional example, and this is something that was created here in Toronto by Paul and Mosher, is fields that have two frequency components, a field, a frequency omega, and its second harmonic, 2 omega. And now, if you shine this laser field and you look at the nonlinear response, and you, for example, calculate the photoinduced dipoles or the photoinduced currents, and you time average because you want an effect that survives time averaging, the lowest order effect that you get is to the cube of the field. And when you take the third power of that field, what happens is that you get this phenomenon of harmonic mixing, in which these frequency components start to mix. No, so you start getting things like omega plus 2 omega minus 2 omega, sorry, omega plus omega minus 2 omega, and that will give you a zero frequency or a DC component in the response. So this is a type of rectification effect in which the sense in which your drive is an AC source and your response is a DC effect. But very importantly, just by changing these laser phases, the relative phase between the omega and the 2 omega component, you can choose the direction of your symmetry breaking. You can induce dipoles to the left or to the right. You can induce currents to the left or to the right. Okay. Now, how experiments are done, this is the traditional way, but how experiments are done right now is that they don't use these continuous wave, very long excitations, but they use laser fields that look like this. Let's see, where's my mouse? I think I managed to lose it. Okay, they use laser fields that look like this. This is the electric field as a function of time. And you see that these are laser fields that are so short that they just have a few cycles in them. No? And these are called few cycle laser fields. And you can think about them as I wish I had my mouse. Where did it go? All right. You can think about it as some amplitude f of t, some envelope, and then a cosine function, no, in the middle. And there's a phase of how this envelope is related to that cosine function. And that phase is the carrier, what is called the carrier envelope phase. When I was a PhD student, controlling the carrier envelope phase was science fiction, no? But now there are several labs that can control it, and they use it now for control. The reason why we want to do things with few cycle laser pulses is because you can apply very strong laser fields before inducing dielectric breakdown. No? So you can access what is called a non-perturbative regime of the light-matter interactions, something that cannot be captured by finite order perturbation theory, before breaking the material. You can apply electric fields of 0.1 to 2 volts per Armstrong, or intensities of 10 to the 11 to 10 to the 13 watts per square centimeter. And what is very interesting about that regime is that if you look at the light-matter interactions, it becomes comparable with the strengths of chemical bonds. So now you can use your laser fields to dress your material and completely distort its electronic structure, and then create a novel laser dress material with effective properties that can be very different from what you observe near equilibrium. Now, these laser fields obviously give you control on a femtosecond time scale because the whole laser field is a few femtoseconds. But very importantly, they also give you control on an attosecond time scale. And the reason for this is because your whole control doesn't depend, when you do resonant physics, continuous wave, what you care about is the envelope of your laser field. But for these very strong laser fields, what you care about is the instantaneous value of the electric field. It feels the whole instantaneous value of the electric field. And now your control may not be due to the whole laser field, but maybe, for example, because your field is very intense right here, and your control may be just because of this peak of the laser field. And because of that, you can now control electrons on attosecond time scales. For reasons that I care very much about, this gives you very large Stark effects strong enough to take dielectrics, for example, fuse silica glass into a metal for a very short period of time. It's a very large event. Now, the main control in these experiments is controlling this carrier envelope phase. And what you do when you control the carrier envelope phase, this is a plot of the laser field for different carrier envelope phases. And you can see that if just by tuning the carrier envelope phase, I can have a field that, for example, it's symmetric with respect to time inversion right there. Or you can have a field that is, let's see, this works. I have to. Or you can have a a field that is antisymmetric with respect to time inversion. And because you're changing the temporal symmetry of the field, you're also changing the degree of laser-induced symmetry breaking that you're generating. So just by changing the scalar envelope phase, this gives you control over the directionality and magnitude of the currents. Okay. So I will claim that the first proposal to use the subcycle structure of light to control currents along nano junctions was done by me in collaboration with Paul as a PhD student. No? Eventually, this was 2007, and there were many unknowns at this point. Eventually, this led to an experiment that changed my life, the experiment Ferencz-Krauss, in which they induced currents along gold silica gold nanojunctions using these few cycle laser pulses. Then, after that experiment emerged, we spent maybe 3, maybe 4 years doing simulation work, trying to understand every nook and crack of that experiment, and then trying to connect it with the original proposal that we had in 2007. And it turned out that the main mechanism was about the same. Okay. And since then, there has been significant experimental and theoretical work in this area. People have now used light to induce currents along graphene-based junctions. This is my main collaborator, Peter Hommenhoff. People now use this type of schemes to do STM imaging, but on an ultra-fast timescale. No? People now use gold nanostructures to shape light, and then use very weak fields to do strong field effects. We have now developed these schemes as a way to measure electronic decoherence directly through a purely electronic observable. So I think there are many good things happening right now in this area. So what I would like to tell you about today, it's a collaboration, perhaps one of the greatest collaborations of my life, between the group of Peter Hommenhoff, the experimental group of Peter Hommenhoff, and in particular 2 PhD students, Tobias Bulaki and Kristen Heide, and my group, and the hero, the computational hero of the group was Antonio Garzón, that did all the simulations that I'm going to show you now. Okay. So here's the hypothesis, and this is the way that I like to do science. We start with a hypothesis. So the hypothesis is that if you have an electric field of light that is antisymmetric with respect to time inversion and few cycle laser pulses, for that you need a carrier envelope phase of pi halves. You will generate real charge carriers, and I will explain what this means. And if your field is symmetric with respect to time inversion, and for which you need a carrier envelope phase of 0, you will generate virtual charge carriers, and I will also explain what this means. Okay, so by real charge carriers, what we mean is the regular photoexcitation. I come in with my laser field. I create electron hole pairs. Yeah, because the laser field has a low temporal symmetry, I give a kick to those electron hole pairs. Electrons will move in one direction, holes will move in the other one. They will travel to the gold electrode, and they will be collected to form a current. Yeah, that's the essential idea. But the main thing is that these excitations survive after the laser pulse. I excite them with my laser field, and they remain. The system remains excited once that laser field is on. The virtual charge carriers are different. The virtual charge carriers are, the idea is as follows. So you see, this laser field, it's more intense for positive amplitude than for negative amplitude. No? And now what the laser field is doing is that it's creating a polarization response in your system. You get this even in non-resonant processes. No? So you're driving your electronic cloud, but you will drive it more strongly in one direction than in the other one. And now, if you didn't have gold electrodes, this is a non-resonant phenomenon. And without the gold electrodes, what will happen is that once your laser field is done, this effect will just go away. Yeah. So in a way, you get laser-induced symmetry breaking during the laser field, but it's due to virtual charge carriers because at the end of the day, you don't excite them. So this is similar to the idea that when you're driving with a laser field, you populate the excited states of your system transiently, and if you have a non-resonant process, that population will just go to 0 because you don't have any resonant processes to transfer effective energy from the laser to the material system. Okay, but now if you connect it to gold electrodes, what happens is that you're shaking this electronic cloud. Your electrons will move more in one direction than the other one, and remember that this is a nonlinear effect, so small changes in the intensity can have a very large effect on the polarization. And now they will hit the gold electrodes, and once they get to the gold electrodes, they get trapped by the gold electrodes, and then they'll come back and then form a current, a real current with real charge carriers. Okay. There was some evidence for this hypothesis. The first evidence was a symmetry analysis that we did here with Paul, in which this is for continuous wave laser pulses and closed systems, in which we showed that if a field was symmetric with respect to time inversion, you could not generate any net momentum that will survive time averaging. Yeah. And for me, that meant that no real carriers were possible. And we also showed that if your field was antisymmetric with respect to time inversion, you could not generate net dipoles that will survive time averaging. And for that, this meant to me that no virtual carriers were possible. But there were problems. This analysis was for a continuous wave pulse in a closed system, while the experiments are done with few cycle laser pulses, which are very different than continuous wave pulses, and in a manifestly open system because you're driving currents. Yeah. The other piece of evidence that we had were two experiments. There was the experiment of Ferenc-Krauss. This is gold, silica gold. And the main thing is that this nanojunction is 50 nanometers, very small. And what they measure is the amount of charge that they extract as a function of the Kerr envelope phase. And you see that it's oscillatory with the Kerr envelope phase, but the maximum is right here at 0. The maximum charge that you extract it at a phase of 0. And right at pi halves, which will be here, they get no net charge. And what I'm pointing out is the black line. That's the one that we should be looking at. Okay. There were also experiments in graphene nanostructures, and these were related but very different in the sense that instead of being 15 nanometers, it was a 5 micrometer nanojunction. And these were done by Peter. And what they were doing, what they like to plot, is that they like to plot the current, and radially they increase the amplitude of the laser field from 0 to 1 to 2 to 3 volts per nanometer. And they plot the maximum of the current, and they can measure the phase at which they do that current. And you see that the maximum current is at the phase of pi halves or 3 pi halves, but at the Kerr envelope phase of 0 and pi, they get very little. Okay. So two very related experiments with a very different signature for the maximum of the control in the Kerr envelope phase. Okay. So we attended this meeting, the quantum control meeting, which is probably one of my meetings. We had just emerged from 3 or 4 years of simulation work, understanding the silica experiments, the Ferenc-Krauss experiments, and the group of Peter was getting ready to publish their paper on graphene. And then we realized that we were talking about the same thing, but they were doing experiments and we were doing simulations. And we sat down in an afternoon and we realized that there was something interesting happening here. We formulated the hypothesis, and this led to many years of collaborations with them, trying to match the experimental measurements in Erlangen with the theory calculations at Rochester. Okay. In order to capture these effects, you need a method that not only gives you the quantum dynamics in the presence of laser fields in bulk matter. No, in this context is graphene. We cannot do graphene. We do graphene nanoribbons. But you also need something that captures whatever is happening at the interface. No? There are several calculations in this field that consider the junction as bulk solids. No? In my opinion, all those calculations are missing all the interfacial effects. No? And they give you an incomplete picture of the actual quantum dynamics. So the right method to do this type of processes are the methods that have been developed by the quantum transfer people, in particular the time-dependent non-equilibrium Green functions methods, because you are able to solve the Liouville-von Neumann equation of your material in the presence of a driving field, and then you can take into account the effect of trapping and injecting charge through these auxiliary terms in the equations of motion. Perhaps the best methods that have been developed that are out there or the most efficient ones are the ones developed by Wang Ho Chen, and this is what we use. Okay. So let me show you 3 years of simulation work in one slide. Okay. So this is the electric field as a function of time. And what I'm plotting here is the charge that you extract as a function of time. So it's not the current, it's the integrated current. I'm taking the current and integrating it over time. And I'm doing a Kerr envelope phase of pi halves here and a Kerr envelope phase of 0. And what Antonio did is that he did calculations with graphene nanoribbons, metallic, with different lengths of 21, 42, and 85 nanometers, so longer and longer junctions. And let me just focus first on the Kerr envelope phase of pi halves. So in this case, you see charge during the pulse is moving up and down. Yeah, sorry, side to side. No, so it just means you're shaking your electronic cloud. Some electrons go into the electrodes, but eventually they go back. No? But once your laser pulse is 0, you get no charge extracted. It goes right at 0. Once your pulse goes away, what you get is charge that increases essentially linearly with time. Yeah. So basically, what that is telling you is that you've created an electron wave packet, with your laser field, and that electronic wave packet is now traveling to the gold electrode and is being collected, which is giving you an increase in charge. But once that electron wave packet hits the gold graphene interface, some of it bounces back. Yeah. And because it bounces back, you see this oscillatory structure in the charge, and eventually it settles to a finite value. If you go from a small junction to a large junction, what you see is that the larger the junction, the bigger the effect, because your photoactive area is increasing. But you also see that these oscillatory structures become faster when you have smaller junctions, simply because it takes less time for your electron wave packet to travel back and forth in your junction. Okay, so the magnitude of the effect increases with length, and all the charge that you extract is after the laser pulse. So this is what we will call real charge carriers, in the sense that I'm generating excitations that survive after the laser pulse, and then I'm collecting it by the gold electrons. Okay. Now, let me focus on the Kerr envelope phase of 0. So here is the same idea: charge as a function of time, different lengths, and what I see is that all the effect, all the symmetry breaking happens during the laser pulse. Yeah. After the laser pulse, nothing happens. No? So I am just shaking my electrons. I'm turning them into a current because I get a net polarization in the problem. But all that effect happens during the laser pulse. After the laser pulse, nothing happens. So this is what we call them virtual charge carriers. And very importantly, this effect is independent of length, because it's an interfacial effect. If your junction increases in size, the effect is approximately of the same magnitude. So if this whole thing is correct, what we should see is that if we go from a small junction to a bigger junction, for the small junction, these interfacial effects, this virtual charge carrier, should be important. While for the longer junction, these real charge carriers should become dominant, because this effect becomes bigger and bigger and bigger as the system size increases. Okay.
Is it the charge collected at one electrode or
at both electrodes?
It's a sum.
Yeah, so in your term you will have the current at the left minus the current at the right, yeah, electrode, and then you're integrating over time to get the net charge that passes through the junction.
Okay, so it's a net.
Huh? It's a net charge passing through the junction. Yes. So yeah, so I'm not showing you what happens at each of the electrodes. I'm showing you the net effect. Okay, so if this whole thing is true, what we should see is that as we increase the system size, these virtual charge carriers should become more important, while these real charge carriers should become more important, while these virtual charge carriers will not change very much with length. And then we should see that the phase of the control should go to pi half. Okay, so let's see how this. Oops, I'm sorry, the wrong button. So this is the experiment exactly that they did at Erlangen. So what in particular the hero here is Toby. So what they did is that they created a junction with 1 micrometer in length, 2 micrometers in length, and 5 micrometers in length. And they measure these currents. And again, they have these radial plots in which I'm plotting the intensity of the current, and the arrow tells you where the peak of the current is. And what you see is that for very large junctions, the peak of the current is at a phase of pi halves. This is what they have seen before. But as they make the junction smaller, the peak of the current starts to shift more and more toward pi or 0, whatever you want to see. So what you're seeing right here is a change in the mechanism between real charge carriers for larger junctions to virtual charge carriers for the smaller junctions. No? Okay, so we were very excited about this because we had figured out that there were 2 mechanisms to induce currents, and that we could disentangle these 2 mechanisms and address them individually just by changing the Kerr envelope phase. So we sent it to a nice journal, and then Toby, when we sent it in the last paragraph, said that because he had control over these 2 mechanisms, that he could create logic gates that operated on an ultra-fast timescale. But I think he wanted to get beyond the editor, no? And the editor said, okay, that's phenomenal, that's super exciting. Why don't you show me that that's the case? So he closed his door, and 3 months later, or 2 months, 3 months later, he arrived with this. So what did he do? He had a junction. This is one of the larger junctions, it's 5 micrometers. And he put a laser right in the middle, A, that will induce these real charge carriers. And he will put a laser right at the interface, B, that will induce these virtual charge carriers. And now he could choose the phases, for example, the phase of A to be pi halves or minus pi half. If it's pi halves, it will move in one direction, say the right. And if it's minus pi half, it will move in the current will be in the opposite direction. And for B, he chose the phase to be either pi halves, in which nothing will happen because it's an interfacial effect. And while for a phase of 0, you will get current in that direction in this particular example. Okay, so he could have situations in which, for example, the currents will, this one will go to the right and this will be 0, and this corresponds to this particular current in this plot that plots for technical reasons the absolute value of the current. Or he could have situations in which the currents both cancel out, and this will be this particular value. Or he will have situations in which the current goes to the left, like this, and so on and so forth. Okay, so now you can assign a logical value to the phase of the laser field. So you can say that if your phase for A is pi halves, I will assign it a logical value of 0. And for B, if it's pi half, I will assign it a logical value of 0. And if it's minus pi halves for A, I will assign it a logical value of 1. And if it's 0 for B, I will assign it a logical value of 1. And then you can have an outcome of this, which is the current. And the current, if it's positive and greater than certain threshold, you say that it has a logical value of 1, and otherwise it's 0 if it's negative or if it's below that threshold. And then you quickly realize that you can have now a logic gate, yeah, in this particular case, an OR gate. But the twist is that this logic gate operates at the femtosecond timescale, no? So in essence, this is the fastest logic gate or information processing that has been created. And because of that, we got this paper into Nature, which was very, very exciting for us. Okay, so let me conclude this part. The dynamics of electrons can be controlled in ultra-fast timescales with few cycle laser pulses with stable carrier envelope phases. These currents, there are two contributions, one coming from what we call real charge carriers and another one coming from the virtual charge carriers. These two contributions, you can disentangle them and address them individually just by varying the carrier envelope phase for the driving lasers. And because you have this, with this augmented control landscape, you can now develop logic gates that operate at femtosecond timescales. And in fact, we told you we did all possible logic gates in this setup. A more personal perspective of what this has meant for me, you see, this for me started like the dream of a graduate student, many years of work put into this proposal that eventually led to very exciting experiments. These experiments led us to do better theory of how to capture them. And eventually, because of our understanding to this better theory, this led us to the discovery of new phenomena and new technologies. No? So it has been a long, long process. No? So let's see, how much time do I have? Maybe 20 minutes or something like this? Okay, so I only had 40 minutes for the talk because we started at 1:10, at 11:10. Let me see how much. Let me try to get to this other topic, which is I want to tell you about the analog quantum simulation of chemical dynamics. So I don't think I need to motivate to describe that chemistry is a dynamical science. As we look at chemical reactions, we look at the dynamics of electrons and nuclei according to the rules of quantum mechanics, and in particular the time-dependent Schrödinger equation. And as people in this room know much better than me, the problem with quantum dynamics is that the computational cost of doing quantum dynamics increases exponentially with system size. And you can see this. You can see this in many ways, but you can see this many-body problem. For example, if you ask the question of the memory needs just to store the wave function. So if you have a wave function in the dimensions, and you say that you're going to represent that wave function in a grid, and that grid will have 100 points per direction, and you just look at the memory needs for this as the number of dimensions increases. So for one dimension, you need 100 points. For 3 dimensions, you need 100 to the 3, and so on and so forth. And you just calculate the memory, and you can really quickly see that beyond maybe 4 or 5 dimensions, there is no computer that can store that wave function just in memory. It's just one aspect of the many-body challenge. And for this reason, there have been many methods that have been developed in quantum dynamics. I mean, Professor Capral has pioneered the mixed quantum classical methods, no? And the people have worked in the split operator, multiple spawning, path integrals, Bohmian exact factorization, the HUM, MCTDH, and so on and so forth. And what I've been interested for now 3 years or so is in an interesting alternative, which is instead of trying to do the dynamics in a classical computer, what we want to do is to get the chemical dynamics of interest and then map this chemical dynamics into a highly controllable quantum hardware, and then let nature do the computations. The problem, instead of the computational part, the problem becomes the map. No, how to establish that map? That's the problem. The advantage of the analog simulation over digital quantum simulation is that it doesn't require a universal quantum computer. No? So the perspective right now is that in the near term, we will be able to do analog simulation. No? It has a possible route to quantum advantage. No? There are many good things, and I'll tell you about our perspective. Now, the idea of doing analog simulation is not new by any means of the imagination. For example, this is an orrery, and this is essentially an analog simulator of celestial motion, in which you crank this lever, and it tells you how all these planets align to one another. So it's a very specific machine for a very specific purpose, no? But it allows you to get all this information that you're interested in. Or for example, when you do hydrodynamics, sometimes computer simulations are not accurate enough, not realistic enough, and then we do analog simulations through wind tunnels in which we get a model of what we want to do, and then replicate the conditions as close as possible to the realistic. Okay. So the problem, the target problem for us has been the dynamics of open quantum systems. And this is a collaboration with Andrew Jordan and John Nicola at the University of Rochester. And the hero of this story is Chang-Woo Kim, who is now an assistant professor in Korea. And so we divide our system we divide our universe into degrees of freedom of interest, in particular electrons and excitons, while our environment will be a bath of thermal phonons. No? And it's the system-bath interaction that leads to the decoherence and the dissipation. So this is the problem that we want to deal with. And the way that we are going to do this is that we are going to map the system energy levels into what are called gate-defined quantum dots. And we are going to map the environment that you can describe as a collection of harmonic oscillators with a given spectral density into an array of quantum electronic circuits, no, with tunable couplings to the system into a concept that we call the quantum bath synthesizer, no, in which we just use this type of coupling to modify how the environment is coupled to the system. Okay. The particular platform that we chose is what are called semiconductor quantum dots. These are not the quantum dots of chemistry. These are how these are done is that you have a two-dimensional, you have a semiconductor heterostructure, and then right at the interface, you get a two-dimensional electron gas, and then you cool it down, and then you deposit electrodes at the surface. So those green and blue things are electrodes, and through these electrodes, you apply a voltage, a potential, and now you can get wells, no, and barriers in the two-dimensional electron gas. And people have been very good about this, and they can, for example, deposit one electrode in one well, in each well, or or 2 electrodes or 3 electrodes. It's a controllable. It's a highly controllable system. So it's a highly controllable Hamiltonian in the sense that I can shape the depth of these wells, and I can also shape the barriers between wells. It has sufficiently long coherence times to enable quantum simulation. It can couple electrically to a controllable quantum environment. And this is very important because electrical coupling is much simpler than, for example, inductive coupling. And this electronic structure can be controlled through what is called a detuning factor. And this detuning factor essentially is the difference in energy between having, okay, so their bread and butter is what is called a double well quantum well, in which you have 2 dots with 2 electrons. And this detuning is the difference in energy between having each electron in each well, E11, minus having the 2 electrons in one of the wells. And the way that you control this is by manipulating the depth of the left dot, epsilon L, with the depth of the right dot, epsilon R. Okay. So these are cryogenic experiments. They operate in temperature, something like millikelvin, no, 60 millikelvin will be temperature. But the type of dynamics that we care about is essentially room temperature dynamics in chemistry. No? So there is a very large difference in temperature between the temperature that we care about and the temperature at which these operate. And that ratio could be something like 10 to the 5. No? So in order to be able to do this map, what needs to happen is that the energy levels of chemistry, they need to be scaled by this ratio. No? So the energies will be gamma times smaller, no? And the simulation time will also be gamma times smaller. No? So if we are thinking about something like a femtosecond type of simulation, then in the simulator, in the actual experimental setup, the actual simulation time, that femtosecond, will have to be multiplied by this factor gamma, which will be 10 to the 5. And now, with that idea in mind, you can take a look at what are the type of requirements for chemical dynamics, for example, of photosynthetic complexes, and what that means in terms of the experimental setup. And then you realize that by the typical ratio of 10 to the 5, you are right in the regime in which the experiments can operate effectively. Okay. Now, the problem that we are going to focus on is one in which we have 2 dots with 2 electrons. And in that problem, there are 5 states, 2 singlets and 3 triplets. The 2 singlets will be ones in which either both electrons are different dots with opposite spin, or both electrons are in the same dot with the opposite spin. These 2 singlets hybridize, no? And in particular, they hybridize, the degree of hybridization is controlled by the barrier, this barrier, and that barrier is called what is called the tunnel coupling. So this is the energy of that singlet state as a function of the detuning, and that hybridization right there is determined by this tunnel coupling. And there are 3 triplet states, the triplet minus, triplet 0, and triplet plus. So 5 states, we need 2, so you have to choose, no? And depending on what you choose, the requirements of your simulator can be very different. So we choose singlet 0, the ground state singlet, and triplet minus for our simulators. And every other level in the simulator will be an spectator state. We don't want to deal with them. So now our target molecular Hamiltonian will be something that looks like this, in which this is the excited state, that's the ground state, that's the energy difference, and then we have some coupling between them. The energy difference between the 2 levels is easy to achieve. You can control that energy difference through the detuning, and you can also control it by applying a magnetic field that shifts these energy levels of the triplet states. So that's easy. But in order to get these off-diagonal couplings, something that connects the singlet 0 with the triplet minus, you need a magnetic field gradient along the direction of growth of the quantum dots. And this is the reason why we put this magnetic field gradient. So each dot has a different quantum dot along that x direction. Okay. Just as in regular simulations, you have parameters, for example, the accuracy of your simulation. In these analog simulations, we also have simulation parameters, and in particular, there is this quantity called the simulation sensitivity. And the simulation sensitivity tells you how much the energy difference between the 2 simulator states, singlet 0 and triplet minus, changes with the detuning, that difference in energy between the left and the right dot. Depending on your simulator sensitivity, their physical requirements for the simulator can be very different. So this is a target feature of the simulator. So now, once you choose your simulator sensitivity and your tunnel coupling, which is also something that you have a choice, now, given parameters for your molecular Hamiltonian, I can tell you how to choose the detuning, the average magnetic field, and the magnetic field gradient in order to map any 2-level system that you care about. Okay, so now we have to work about the environment. And so the question is, why quantum electronic circuits? So when you have an electronic circuit that has a capacitive coupling and an inductance, it turns out that you can store charge in the capacitor proportionally to the charge. You can store energy in the capacitor proportional to the charge squared, and you can store energy in the inductance in the inductor proportional to magnetic flux. So you see, this looks exactly like a harmonic oscillator. And in fact, this charge and flux are canonically conjugated variables. And people in condensed matter physics know this very well. We've been learning about this. So this behaves exactly like a harmonic oscillator. And if you cool it low enough to low enough temperatures, it behaves like a quantum harmonic oscillator, where now the position will be the magnetic flux, the momentum will be the charge, the mass is the capacitance, and the frequency is determined by the ratio between the inductance and the capacitor. Okay. So what's the dynamics? Under relatively general conditions, we can think of environments in chemistry as collections of harmonic oscillators. No? Even for things that are unharmonic. And the reason for this is because what you care about is how that environment responds to the influence of the system, and that response can be harmonic even if the environment can be very complicated. So you can think about it as a collection of harmonic oscillators. And now we will map this into arrays of quantum electronic circuits. Now, those arrays of quantum electronic circuits, because they're quantum harmonic oscillators, they will lead to 0-point fluctuations of the charge. And if you have 0-point fluctuations of the charge, and you just connect that quantum bath synthesizer to just one of the dots, what this will do is that it will lead to fluctuations, to quantum fluctuations of the depth of that, say, left dot. And through that quantum fluctuations of the depth of the left dot, it will lead to quantum fluctuations in this detuning, and this will lead to dephasing and dissipation. Yeah. Okay. So if you look at the spectral density of this type of circuits, well, I mean, when you have very sharp circuits, you get very sharp peaks in the spectral densities. But now, if you introduce a resistance, what happens to that peaks is that they get broadened. No? And now with this LCR circuits or RLC circuits, now you can think about having, for example, the spectral density of a chemical environment, which is a complicated thing with many peaks at high vibrations and a low frequency vibration. It's very complicated. And you can decompose it in terms of circuits operating at different colors. And what we have done is that given a spectral density that you have targeted in, I can tell you how to choose the impedance of the circuit in order to match it. No? Okay. So then comes the question of how well does this work? So we did emulate the simulator with the 5 levels using the hierarchical equation of motion for the connoisseurs using low temperature corrections. And what I'm plotting here is the population inversion. We start in the excited state and we see how the population goes down for different simulation conditions, the fidelity of the simulation, and the leakage. And you can see that you can choose conditions, in particular simulation sensitivity and tonal coupling, in which the dynamics that you get in your simulator, which are the color lines, get very close to the target dynamics, which is the black. No? So it can be highly accurate. When you see that it fails, is because your population is leaking out of the simulator space. So you have 5 levels, and you have only 2 that form part of the simulator. And when population leaks out of those states, that's when it fails. So for example, this red one, which is the worst simulator in that case, is because you see that if you look at fidelity, the fidelity is decreasing, and is mostly because you have leakage into these spectator states. Okay, so we actually tested the whole parameter space, and here what I'm showing you is the fidelity, the minimum fidelity, as a function of sensitivity and tonal coupling. And without noise, what you see is that you can get sensitivities that are very large and tonal couplings that are very large. This will be the upper blue line here, and those are the ones that will give you the better efficiency. But now you will ask the question, okay, you know what, these quantum dots are pretty noisy. Will this analog simulator work in the presence of the natural environment of the system? So we included the noise, and this is what I'm showing you right here. So with noise, the simulation is worse, of course, than without noise, but still the fidelities here, even in the presence of noise, are larger than 99%. So it's pretty good, no? And then there is an optimal sensitivity and an optimal tonal coupling for this particular problem that leads to the most accurate simulation for this particular problem that we deal with, which is simple. It's a Drude-Lorentz spectral density. Okay. In terms of experimental requirements, what do we need? We need a coherent double quantum dot and spin charge hybridization. That we know how to do. Spin charge hybridization, that means that we are using this singlet, triplet minus states. Yeah? We need large local magnetic fields. That we also know how to do. we need quantum resonators. That means these electronic circuits interacting with the quantum dots. This is where the experiments are. This is what they're trying right now. And we need arrays of high impedance quantum circuits for color. And in particular, we need about 100, 1 to 100 per color. No, this is a challenge. No, there is nothing impossible here. No, it's possible with current technology, but it's still experimentally challenging. Okay. So let me summarize. We develop a useful map for the analog quantum simulation of two-level molecules in interaction with a thermal environment. The model parameters can be experimentally tuned. It fully captures the decoherence due to fully quantum harmonic environments of arbitrary complexity. It can go beyond Lindblad, Redfield, and even the hierarchical equation of motion treatments of the dynamics of open quantum systems. And the reason why I say that it goes beyond the HEOM is because the HEOM has a really hard time computational to capture environments that are very complex. The more features they have, the more complicated the dynamics becomes. Okay, so with that, let me thank you for your attention. Thank my group at the University of Rochester, really an amazing gang, the NSF for funding, and I thank also my collaborators. Yeah.